So welcome. So the first talk of today will be given by K V Subrahmanyam from CMI, and he'll talk about invariance, compression space, and Brascamp-Lieb inequality.
Thanks to Meena, Satya, and Neeraj for inviting me. This will be work really related to what I was involved in some time ago. But this work is largely due to Ankit Garg, Gurwitz, Rafael Oliveira, and Avi Vigderson. So I will. So at least the part about BL inequalities is entirely theirs. So what I would do is I will introduce the problem, and one reason to actually pick up this topic was because so my interest for this came from GCT, and GCT is generally concerned with group actions on varieties, and so one can pose similar questions actually. So in that sense, this area is rich in questions. There are a lot of questions which one can ask. And the other interesting aspect of at least how this problem was solved was that it is an interplay of sort of diverse areas. So three areas sort of meet at a point, and you seem to require all three. So I hope at the end of this I would motivate you enough to maybe take and start reading at least group actions, because the problems are very easily stated, but the algorithmic issues are not easy, and I think it will involve some good mathematics and some non-trivial algorithmic skills to solve these problems. So this was the reason I picked up this. The motivating problem for me, as I said, was through GCT, but before I introduce that, let us look at the following question. So I have a collection of matrices A1, A2, AM, and we all know that the following problem of testing whether the determinant of this formal sum. So now when I look at it, so each of this is an n by n matrix. So finally, when I write it down, you get n by n matrix whose entries are all linear forms in the variables x1 to xm. And you want to know if the determinant of this is not 0. So this, of course, we know is a very central problem, and a solution to this by the work of Cabanets and Impagliazzo actually tell you that you can get good lower bounds from this. So this is really a central problem that we would love to see solved, but we are still far away from it. So the question that one could ask is, what happens the xi's come from are non-commuting? Yeah. So we went through a lot of talks yesterday with spoke of non-computing in the skew field, and you can ask the same problem there. Suppose these variables were non-commuting, then one would like to know if this is identically 0, and so this is the way actually GGO W sort of came to this problem. So they were interested in solving this problem in the case when these variables do not commute. And so I will not go into the details of free skew fields, because it was reasonably well done yesterday. So as far as I am concerned, these are non-commuting variables, and somehow we would like to know when we don't allow normal cancellations that we allow with commuting variables, namely x1, x2 is equal to x2, x1. Can one still test whether this is, and the reason one expects this to be easier is just the intuition that things in the non-commutative world are perhaps simpler. I mean, this is the reason, I think. Yeah. So it turns out that in the non-commuting, so this problem was actually, so it turns out that there is when I'm looking at this question over the over variables which commute, then really one is asking whether the formal determinant as a polynomial over So this, of course, you could pick up your favorite field and ask the same question, whether this polynomial is non-zero as an element of this field with variables x1, x2, xn thrown in, this field extension, and one would like to know if in the polynomial ring over the field it is not zero. The corresponding question in the commuting world is whether it is not zero over the skew field. Yeah. So it turns out that there is a very
You mean the ring or
this is actually the skew field itself. We are looking at the skew field. So whatever they put, what would they put something else? No? Another bracket. Yeah, they put this. Yes.
What is that? The first page, the fraction field.
Fractional field, the fraction field of, and it has to be carefully done because we are working over non-commutative with non-commutative variables. So then what does it mean for one expression to be equal to another expression and so on? So that has to be formalized. So I'm not going to get into.
So what is the difference between this angle bracket and the bracket?
No, here the cutting is the usual fractional, function field where the variables commute. Yeah, that would be the usual notation. Whereas here, the field of fractions. Whereas here, we are looking at non-commuting variables. So that is the only difference. So so this notation is introduced primarily in the for when I'm looking at these variables as non-commuting. Yeah. Okay. So it turns out that over this there is a characterization which is the following. So theorem now det of, so if I call this matrix A, yeah, the matrix, this is what I call A, then det of A is 0 if and only if for all k and all k cross k matrices so like was introduced by Partha, so typically one would have to substitute matrices for x1 to xm in the non-commuting world, and this is what the theorem says, that if I look at so it turns out that determinant of A is 0 if and only if for all matrices, for all k cross k matrices B1 to Bm, it is the case that determinant of B1 tensor A1 plus B2 tensor A2 plus Bm tensor Am is 0, whereby B1 tensor A1, I mean, so if I have a matrix B1 and I have a matrix A1, then this tensor product is real. So this is a k cross k matrix. This is an n cross n matrix. So we set up an kn by kn matrix. What you do is you take the first entry here and multiply it with this entire matrix and put it here. Then take the second entry, multiply it with this entire matrix and put it here. And do this for every entry in the matrix, and you get a really large matrix here. Yeah. It is the diagonal action on the corresponding tensor, yes. So, yeah.
What is the determinant in this context?
This is here, this is the commuted. This.
Yeah, but the first in the theorem.
The det of A in the non-commuting world.
Just which one? I mean,
Of this big matrix. A is equal to x1a1 plus x2a2 plus xmam. If I'm looking at this as a, sorry?
But it's not only you have to define
Does it matter? Yes. So when I actually formally when I'm going to do this, finally it really does not matter. This is
monomial, each monomial, I guess you write it in row 1 and then row 2 and then row 3.
which one? Yeah. So when I'm looking at this, so you can imagine. So okay, the definition of the determinant there. So you, yes. So you will actually formally write it as sine sigma. So you will write x1 sigma, x2 sigma 2, x. So determinant of x, let me call it. So maybe capital D or d of x here in the non-commutating word, or maybe y, I mean a matrix y, because there were x's there. So you'll write the entries as Ramprasad said. You'll write the entry of the first row that you picked up, then the second row, then the third row, and so on. And this is the way you will expand it. Yeah. Yeah. And here we are saying, well, I plug in these matrices, and then I evaluate it as a determinant as we are used to, as in determinant, you expand it, and you're allowed. So these are now, of course, entries over the field. So B1, B2, Bm are matrices that you picked out from your base field F, and you evaluate this. And there, of course, we know everything computes, so there is no problem. So you can actually calculate this and check if. But of course, this is the question is how large should I take my B's to be, and to be able to conclude that in fact this determinant actually is 0. Yeah. Now, so there are, just like in the commutative world, we know that the determinant of a matrix is 0 if there is an R less than n such that the matrix splits as a product of an n cross R matrix and an R cross n matrix. There are similar theorems here also in the non-commutative world. Yeah. There, of course, the entries will now be entries in the skew field. Yeah. So you can write. So determinant will be non-zero if will be 0. Sorry, if there is an R less than n such that I can write it as a product of a matrix of size n cross R and R cross n. So there are all those sort of similarities actually. Okay. Yeah. Yeah. Are just entries, are elements over n cross n matrices with entries in F. Entries in F. Yeah. So when I take this, then every entry in the matrix A is a linear form over the variables x1, x2, xn. So this is the standard PIT then, and or DIT ID. Yeah. Okay. So this is the connection. So at this point, it turns out that this is the connection with invariant theory. So I'll introduce the first character here. So this is the connection with invariants, which I will describe soon. Yeah. So let me briefly recall, if you have a group G and a space X, then we say G acts on X if there is a map from G cross X, G definition, G acting on X. So this is the notation we use. G acts on X if there is a map of this kind, which has the property that if I look at the action of G1, yeah, then this must be the action of G1, G2 on X. And so therefore the identity fixes every element, and if I first act for all X, this should be true. All X for all G1, G2, and G, we need this to hold. So if I first act G2 on X and then I act G1 on the resultant that I get, that should be really the action of G1, G2 on X. So if this happens, then we say G is acting on the space X. So typically in GCT, one looks at spaces X, which are nice. They're typically either going to be projective spaces or nice affine spaces. And the G that one considers there are nice groups. Typically, one would look at GL, NC, SLNC. So these are the typical groups that one considers, namely invertible matrices over complex numbers, or invertible matrices over complex numbers with determinant 1. So these are the groups that one is interested in. Yeah. So the connection, as I said, with invariant theory is the following. So I could just start with the same collection of matrices, but I'll write it this way now. A1, A2. Maybe at this point I'll not. Maybe I won't call it A1, A2, AM. Suppose I just give you a collection of matrices Z1, Z2, Zm. Now this, when I think about this space, these are all again n cross n matrices. And if I look at the action, so here I'm at this point not going to tell you what the entries of these matrices are. For now, let us assume that the entries of these matrices are variable entries. Yeah. Then I can look at the action of SLN cross SLN on this M tuple of matrices. These are all n cross n matrices. And the action of this, when I want to specify it this way, I need to tell you if I give you a collection of M, if they were honest matrices over my base field, then this gives me an action. If I look at a tuple A comma B from here, this can send this to A1 Z1 B transpose, A Z2 B transpose, A Zm B transpose. So if I give you an M tuple of matrices over my base field, then I can get to this. Yeah, and one can check that this satisfies the definition of an action. Yeah. So now when I think of these briefly as matrices with indeterminates, I could ask the following question. Yeah. Under this action, what polynomial functions in the entries of Z1, Z2, Zm. So as I said, briefly think of these as matrices with indeterminates. Then of course also there is an action, SLN cross SLN sends this to some linear combination of the entries in Z1. This also sends it likewise to a linear combination of the formal variables that are present in Z2 and so on. Then I can ask the following question. This is the motivating question of invariant theory actually. What polynomial functions in the entries of the variables in Z1, Z2, Zm are preserved or are invariant under this? Yeah. By this, what do I mean? Well, from here, under the action of AB, so look at the action of SLN cross SLN on this collection of matrices. So every pair of matrices is going to send this point to some other point. And I'm going to evaluate a function in the entries here, and I'm going to evaluate the same function in the entries here. And I want to see if these functions are the same. So for example, if I look at determinant of Z1, determinant of Z1 is of course going to be invariant because this matrix has gone to this matrix, and the determinant of A Z1 B transpose is in fact the determinant of Z1. Yeah. Likewise, determinant of Z2 is also preserved. A little thought will tell you that the determinant of this is also preserved actually. Yeah, if I take this 2n by 2n matrix and I look at what happens to this determinant, this under the action, if so I get a certain polynomial, yeah, of degree whatever 2n. If I look at this as a determinant, if I calculate the same thing there, it turns out even this is preserved. Yeah, so I can allow even this is going to be, so any, you can check that this will also be preserved actually. Yeah, so it turns out that the invariants are nicely described in this case. The invariants are in fact exactly this. They are going to be B1 tensor Z1 plus B2 tensor Z2 plus Bm tensor Zm. So I can take arbitrary matrices over my base field, yeah, tensor it with Z1, tensor it with Z2, tensor it with Zm, take arbitrary matrices B1, B2, Bm over my base field, take this big determinant that you get and evaluate this. Now this will give me of course a polynomial in the entries of Z1, Z2 and Zm because these are honest matrices over my base field. So I'll get a polynomial over my base field with coefficients, a polynomial in the variables of Z1, Z2, Zm with coefficients in my base field, and these are going to be invariant. And in fact, there is a theorem due to a lot of people, Schofield in 92, which shows that in fact this completely characterizes the ring of invariants. All invariants are of this form. Yeah. Okay. So then it really tells you that if I look at
All invariants are generated by these?
yeah, all invariants are polynomial functions in such invariants. Yeah. So this is if you plug in this, get an invariant, plug in some other collection of matrices, and take polynomial combinations of those invariants, you get all invariants. Yeah. So another class. So now this motivates another classical question in invariant theory, which is the following actually. Sorry. This well, at this point I'm looking at only complex numbers, but it turns out this is true even over finite fields. Yeah. Yeah. So for this talk, I'm only going to consider complex my polynomials as coming. My f is going to be c actually. Okay. So then there is another question one could be interested in. Okay, take the collection of all polynomials that are invariant, and then one could ask, if I now give you a1, a2, am coming from with entries in my field, one could ask the following question: is it the case that for this choice of a1, a2, am, all invariants vanish on this tuple? That is, when I actually plug in for the polynomial I get here, I plug in the entries of a1 for z1, the entries of a2 for z2, and the entries of am for zm. Is this polynomial 0? Yeah? And is it true for all polynomials which are invariant? Yeah? So the question is what is called the null cone question. So the null cone is, in this case, set of all m tuples of n cross n matrices over whatever my f, such that all invariants vanish. Okay. So then this question of whether this determinant is 0 is really asking whether a1, a2, am is in the null cone for the given action. So it is just a reformulation of the same question. Yeah, because this characterization says that determinant vanishes precisely when no matter what b1, b2, bm I take, I will get 0. Yeah, and yeah, so this is the connection with invariant theory.
Is this a proof of the theorem?
Which one?
So what you just said, does this prove?
No. So one has to show that the null cone precisely is matrices of this kind and so on. So the null cone one can actually show that if I give you this particular action, then the null cone is precisely defined like this. Yeah. So the definition of the null cone, no. So then if you believe this, then the definition of the null cone is precisely, then this tells me that the null cone is the collection of all made points. But one would like a better characterization of the null cone.
So you wouldn't have to go into the bounds on K. The theorem can be proved without giving a bound on K.
The theorem, yes, but the theorem will, and ideally you would like to get a bound on K to say at what is the defining set of equations for the null cone. That is really the interest actually. Yes.
The only functions you're interested in are homogeneous functions. Otherwise, just take the constant as
Which one? I am looking at only homogeneous invariants. Yes. homogeneous invariants. I am only looking at homogeneous invariants, the ring of homogeneous. Yeah, so, okay. So it turns out that there is an alternate characterization of invariants of the null cone, which is of importance. So this is again a theorem due to a number of people. Again, Schofield in 92, Dirksen, Wayman in 2000. So various people, so even Bharat, Suresh Nayak and me, we also rediscovered this. So various people have done this in various different contexts actually. So it turns out that a set of matrices, an M-tuple of matrices, an M-tuple matrices is in the null cone if and only if there exists V subset of Cn, W subset of Cn, dimension V is strictly bigger than dimension W. Yeah. So it turns out that there is the alternate, this is the characterization one would be actually finally interested in. A set of matrices is in the null cone if and only if there is a subspace V of Cn and a subspace W. Or, so this is to be thought of as in the image actually. So that with the property the dimension of V is strictly bigger than dimension of W and all the AIs shrink V into W. Yeah. This is the no, that is for a single matrix. But here you are saying a collection of matrices is in the null cone if all of them actually shrink. All of them push a fixed subspace into a fixed subspace. Yes. Yeah. So for a single matrix, that's what it will be. Yes. Yeah. Okay. Yeah. So which means that this brings us to compression spaces. So this has been introduced. Now this has been introduced. Huh?
The first half is universally quantified because talking about all invariants.
Yes, and here you are saying if I can actually find a witnessing shrinking subspace, then you are done actually. Yeah. So, but actually this will be true of all questions over the null cone. This is an important point actually. All questions over the null cone, if I want to check whether something is the null cone, one can show that there is a specific sort of group element which will push it to 0. Yeah, so that actually turns out to be true. Yeah. So then a subspace like this is what we call a compression space because it has been compressed. Yeah, and if I look at the difference between the dimension of V and dimension of W, I say if this difference is C, then I say V is a C shrunk subspace. Yeah. Okay, and it turns out that when I want to define the non-commutative rank, is the minimum over n minus C where there is a C shrunk subspace. Yeah. So like I said, if I give you a collection of matrices and I construct this formal object over this Q field, if it has rank R, then I can write this matrix as a product of an n cross R and an R cross n matrix. And the rank then of course would be the minimum R for which that happens actually. And it turns out that shrunk subspaces give you this information. That in this case V is called the shrunk subspace and C was the shrinkage factor. So I will say V is a C shrunk subspace. So run over all possible shrunk subspaces, look at how much they have been shrunk by and look at minimum over n minus c for all c. Yeah. So of course, which means that something is not in the null cone. Sorry. Yeah. Yeah. Yeah.
So what is the role of AIs on the first side of the economy?
On the first side, yes. So you are saying these are the AIs that. So I want to determine when a collection of matrices is in the null cone. So one way of doing it is to evaluate all invariant polynomials on them and check that they are 0. The other thing to do would be to identify a subspace V which actually gets shrunk by all of them. Which means in the linear span of these matrices, any matrix that is present in the linear span of these matrices also shrinks this subspace. So that is the role of AI.
And there are m of AIs.
They are
n cross n, but only n seems to play a role on the other side.
sorry? For all I in M, 1 to M. Huh? For all I, AI, so AI runs, so A1 pushes V into W, A2 pushes V into W, AM, all of them have to push.
And is there any bound on the size of V or it's only the dimension?
Yeah, only the dimension because we are looking at, yeah, so I mean, because I have to look at the image of V under AI.
Find a small subspace which moreover has.
No, so if I want, no, actually no. If you can find me a witnessing shrunk subspace, well, I know that it is in the null cone.
So my question is more like this witness may not be small.
No, the witness will be small, right? Because you can actually find a basis.
Okay, so n-dimensional is
Yes. So because these are matrices acting of sending vectors in Cn to Cn. So I can find a basis for V and that is a witnessing basis.
So it's an efficient witness.
Yes, you can actually construct an efficient witness. Yes, it so turns out. Yes.
So for a problem, so the first side of the theorem statement is a problem which, if we go by the null cone definition, would be like for all something.
Yes, and now we have come to.
So you have like an NP test.
Yes, absolutely. Yes, absolutely, absolutely.
So V here you can take the whole space.
Sorry,
So V is the whole space.
but you need it all. You need everything to shrink into W, into the same W also. So that is not clear. So I might have to.
We may be Cn, but I think in the definition of C, you want the C to be the minimum.
No, if V is C and maybe A1 pushes full. So that is not true actually because I have to select this. I have to make sure that every AI sends V into W. That is important.
Why are you looking at min of n minus c? What is
No, with n minus maximum shrunk subspace if you want.
what is
C is the, so there exists a C shrunk subspace. That means dimension of V minus dimension of W is what I look at.
n may not be the dimension of
No. So I should put, n is anyway outside. N minus if you want, max if you want. If you want. Look at the largest shrunk subspace. Look at the subspace which is shrunk most. And
So n is n minus max of dimension of W.
the reduction. So I could have, what I did was also right. I mean, n minus the size of, the shrinkage factor if you want. Yeah, how much?
Dimension of V mod W.
Dimension of V mod W. Yes. Yeah. Okay. So how much time do I have? Not much, my God. Yeah. Okay. So maybe I'll skip the history of this actually, because there is a large history. Yeah. Very brief history. So it turns out that Gurwitz solved this problem in 2004 under a certain promise. Then for rank 1 subspaces, Ivanios, Gimikiao, Karpinski and Nicolas Santa, when each of AI is a rank 1 matrix, they solved this. Then in
Problem
finding a shrunk subspace, yeah, and in 2015, along with Ivanios and Jimmy Kiao, we showed an exponential time algorithm actually to determine membership in the null cone. Yeah. So in fact, it was exactly n plus 1 factorial the way we said it. Then actually GGO W showed a polytime algorithm, gave up poly n, there's only n and m of course. Then actually it turns out that Dirksen and Markham used our result to show that the ring, that the null cone is cut off by polynomials of degree n into n minus 1 is what they showed. Yeah. And they also showed that the full ring of invariants is generated by polynomials of degree n to the 6. So if I look at all polynomials of this kind up to degree n to the 6 and I take their polynomial combinations, I will get every invariant. Yeah. So the ring of invariants is generated in degree n to the 6. Yeah. So then, sorry? This comes via bound on this actually. If I know the generators bound on the generators of the null cone, I get a bound on the generators of the ring. Absolutely. There I can take, yeah. There I can take, yes. So if I then later we actually showed that and degree n times n plus 1 and we do it over all fields. Also reasonable, I mean there is some quantification, I mean I don't want to get into that. Yeah. Yeah. Okay. The null cone is cut off by polynomials of degree n into n minus 1, which means if I look at, yes, so here we showed that the null cone is in fact, so there is a very simple proof. This was a slightly complicated proof. We have a very straightforward proof. Slightly worse than theirs. Simple proof, and it gives you the same n to the 6 actually. So that is not an issue. Yeah.
What does it mean that null cone is cut off by polynomials?
Which means if I look at the zero locus of these polynomials, it is precisely the null cone. Yeah. The set of all points which vanish. Okay. So let me now, what I want to do in the remaining time is to give the algorithm due to GGO W. So they will detect whether something is in the null cone, yeah, but they don't get you a witnessing V and W. So that is one difference actually. Whereas we in our paper are able to get a witnessing V, but we don't calculate something else that they need to calculate. So their approach is very different, it is very analytical, and that is what extends to Brascamp-Lieb. So let me just go there quickly. So what happens is, so this goes back to Synchron in 1964, where given a collection of operators like this, A1, A2, AM, Synchron constructs the following operator defines an L going from positive semi-definite matrices to positive semi-definite matrices. So what does he say? He says send X to sigma AI X AI dagger running over. So consider this operator, which sort of clubs in all the AIs together and constructs an operator for you on positive semi-definite matrices. Huh? Now we are over the real field actually. Yeah. Though this operator even makes sense over MNC actually. Yeah. Then I have to change this to CN MNC to MNC. Sorry, and this, sorry? And dagger is, this is dagger, I mean, this is dagger, yeah. So, yeah, so like Raghavan pointed out, if I'm looking at positive semi-definite matrices, then I have to work over reals. But otherwise this operator makes sense. In fact, this operator is what GGO W consider as an operator from MNC C matrices, n cross n matrices to n cross n matrices. Yeah. Okay. So, okay. So then the connection to shrinkage or belonging to the null cone so then it turns out that a collection of matrices A1, A2, Am belong to the null cone if and only if there exists a positive definite matrix such that rank of L of x is strictly less than rank of x. Yeah. So this is the connection with the null cone formulation, that collection of matrices A1, A2, Am belong to the, and this I don't know whom I should attribute this to. So a collection A1, A2, Am is in the null cone if and only if there is a positive semi-definite matrix, so that when I apply L to this and I get a matrix here, if I look at the rank of L of x, it should be strictly smaller than the rank of x. Yeah? Then A1, A2, Am is in the null cone. Yeah? And this is really what Gurwitz analyzed in his 2004 paper. Yeah? And as I pointed out, Gurwitz only solved this under a certain promise, and what happens is he has to so I will give the details actually. So he defines the notion of the capacity of an operator L, yeah, and he was able to lower bound the capacity of the operator only in special cases actually. So it turns out that this exponential lower bound, in this paper we actually showed that the ring of invariants is generated in degree n plus 1 factorial actually. That bound suffices to give a lower bound on the capacity.
Can you prove that existence of x by taking the projector from the, so you say, so this theorem tells you that something in the null cone if and only there is.
Yeah, actually it is. You can actually get out this x straight from that. Yes, absolutely, 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 absolutely. Yeah, yeah. So the problem with the 2004 analysis was that Gurwitz could not bound what I will define very soon, namely the capacity of the operator L. So I will define that and then give you the algorithm of GGO W and the analysis. I'll briefly indicate the analysis. Sorry? In this case, yes. So this is a characteristic 0 thing, whereas finally, of course, we know it over all fields also by our work. But that works very, very differently. Yeah? So, okay. So what is the capacity of an operator? The capacity of L is defined to be infimum of the determinant of L of x, where the infimum is taken over all x with determinant of x equal to 1. Yeah. Yeah. So the capacity is you apply L to all positive definite matrices, positive semi-definite matrices. Well, in this case, they will have to be positive definite because you're saying determinant of x is actually 1. Yeah. Run over all positive definite matrices of determinant 1, apply L of x, calculate the determinant of L of x, and take the infimum. This is what is defined as the capacity of the operator L. Yeah. And this is the measure that one uses. So the background for is the following. So it turns out that, so this, by the way, is closely related to an earlier analysis of Lineal, Wigderson, and Samronitsky, yeah, where they actually calculate, they give a polytime approximation for the permanent actually. Yeah, polytime, exponent, of course, an exponential approximation, but nevertheless polytime. And the analysis that Gurwitz did in his 2004 paper was really based on their earlier work. So what they did and what Gurwitz did is really just a quantum version of what LSW did. So, and so it turns out, okay, now what do you have? So if, so we say L is doubly stochastic if L of T of L of I is I and L star of I, the dual of L, which is, so I can define, like I defined L, I can define a dual operator which sends it first, which first operates on AI. Yeah, so first you operate on AI. Yeah, yeah. So this analysis depends on the following: that if L is doubly stochastic, then capacity of L is actually 1. Yeah. And so I'll define one more operator, one more operation on this. So if I look at what happens to L of I, yeah, so L of I by definition is L applied to the identity element is AI dagger, I equal to 1 to m. So under some very mild non-triviality conditions, one can show that this, if, I mean, so there are certain AIs which you can detect immediately in the null cone. Yeah, so if I avoid those cases, then it turns out that this matrix is actually invertible. If I avoid those cases which are trivial to check whether they belong to the null cone. So it will turn out they are in the null cone if and only all of them kill a particular vector, actually. Yeah. So then if I look at this, we will, yeah. So we would be interested in the case where this is actually equal to I, so as to make it, in some sense, at least close to doubly stochastic. So what this says is, if L of I is I or L star of I is I, then and L star of I, then L is doubly stochastic. So what these people do is they look at L of I, and if this is not equal to identity, there is a trivial way to modify my operator L by the following, actually. So you can send each AI to take, this is Hermitian, so I can take its square root, send AI, consider these new collection of operators. Yeah? So instead of working with AIs, now I work with these transformed versions. Then you can immediately check that if I call these now AI prime and I define my operator L with respect to AI prime, then it is immediate that L of I, maybe I should call it L prime of I is actually, I have just modified it. So it is like, this is the Synchron algorithm. So this is like multiplying each of the AIs on the left. Yeah, so like it's like a series of row operations that you're actually doing. Yeah, and if L star of I is not identity, by likewise multiplying AI on the right by the inverse of not this but AI dagger AI, one can actually make sure that L star of I then becomes I. Yeah, and this gives you the algorithm, a remarkable algorithm actually. So what is their algorithm? I will just describe that and I'll briefly indicate the analysis. So at each stage. So what they call algorithm G, I suppose, for Grewitz. Do the following. Normalize if, so this is take L and normalize it by row operations. Alternately, you do the following, normalize. So then of course you are going to get a new operator. Maybe you started off with an operator which was, for which L star of I was equal to I, but by doing this process you have destroyed that. So now you, once again, you correct it by doing a set of column operations. You do this for some t number of steps, yeah? And then in the end you evaluate at each, whenever you do this, so you do this, then do this and calculate the distance to the following. Take trace of L of I minus I whole squared plus trace of L star. Take this matrix, evaluate this distance. Yeah. So this is going to be your distance measure. You calculate this as a distance measure, and then you do this for some number t of operations, and you, so if I call this at stage j, this is what you are going to do. You are going to do, so this is for people who are familiar with alternate minimization, this is what is happening. You alternately do some row operations. So typically this is what a lot of optimization algorithms, where you have two sort of conflicting parameters that you need to sort of work with. You need to satisfy this constraint, you need to satisfy this constraint. Then you want the standard alternate minimization algorithm actually satisfies this, then satisfies this. In the process it might destroy this, once again satisfy this. So this is the way the algorithm goes. And this algorithm is precisely of the same flavor. And then in the end you check if for some t, epsilon j is less than 1 by some number 6 to the n, something like this. And if this is the case, then it is actually close to being doubly stochastic. Yeah? And you know, so I have not stated the theorem. The theorem which states that if you are close to doubly stochastic and close in this, yeah. So if you have so at every stage, remember, you are guaranteed that either L or L star of I is normalized properly. So if you have a normalized operator, yeah, which is at most, for which this distance is at most n plus 1 over n plus 1, then you can actually show that this cannot be rank decreasing. Yeah, this operator L cannot be rank decreasing, which means the collection of matrices A1, A2, Am that you start off with cannot be in the null cone. Yeah. But you can do far more actually. So when I do this, I can actually keep track of what is the capacity of this new operator in terms of the capacity of the old operator. Yeah. Now, so this, then you can lower bound the capacity of the starting operator L that you started off with. So you can lower bound it in terms of some exponential of minus n. So it is away from 0. Yeah. And what you can actually show is that if the operator is not non-rank decreasing, that means there is no x for which L of x has smaller rank, and if you are more than this distance away, then by performing this operation, you will actually push up its capacity. Yeah. So you have a lower bound on the capacity, you will push up the capacity by a factor of 1 plus exponential of 1 by n, something like this. You will push it up by this factor. Sorry. So at every stage when I do this, in the end you will check this, and what will happen is if epsilon t is not less than 1 over 6n for every t, then you will report it is rank shrinking actually. You will declare the original operator to be rank shrinking, and you will say the collection of AIs were in the null cone. So this is, no, this is only, I mean, all this is fairly loose actually. I mean, so it keeps repeating this steps, checks this distance and keeps track of this distance. And in the end you check whether you are, how close you are to 0. You will get a bound on T, yes. Because if you have a lower bound, no, you will run it, you have a lower bound. You have a lower bound on this, on the rank, and you know in how many steps, if at every stage, if I knew the original operator is non-rank decreasing, you are guaranteed you are going to increase the capacity at every stage. So therefore, after a polynomial number of iterations, you should be close to 1. You should be close to the identity actually. Yeah, you should be close to being doubly stochastic. And what this is measuring is your capacity vis-a-vis the capacity of a doubly stochastic matrix. That is exactly what this is measuring. So since you have this, you have an improvement, yeah, and you know that. So the crucial lemma is the following: that if either L of I is I or L star of I is I, and L of I minus I whole squared plus trace of L star of I minus I whole squared is less than or equal to some function of n, then L is non-rank decreasing. So this is the crucial lemma that you need to prove. Yeah, and this lemma actually falls out quite easily. I mean, it's not a difficult lemma by any means. So much of this was actually there in Gurvit's original paper. I have not read Gurvit's original paper. It's a difficult paper to read. I mean, but this particular paper is very nicely written. I would recommend anybody to read it actually. Yeah, everybody to read it in fact. GGO W is beautifully written. Yeah, and so therefore they have a polynomial time algorithm to actually even get hold of the capacity, because they have a lower bound and they know after how many steps you're close to that, so you can go backwards and actually estimate the capacity. So this is what they actually do. They can.
KV, I think I don't understand this thing. It's only very straightforward. L is non-rank decreasing. What do you mean?
Is non-rank decreasing means there is no x for which rank of L of x is strictly less than rank of x.
That's equivalent to cap L is 0? No.
That is equivalent to A1, A2, AM is in the null cone or not in whatever, whichever way. I mean,
We stop at that.
yeah.
Then we'll stop.
Yeah, so this lemma allows us to figure out what is the stoppage I require. So we know that if L is non-rank decreasing, if L is rank decreasing, you'll never come here. So if L is if L actually shrinks a particular subspace, then of course this is 0. The capacity of that operator is 0. But if it is rank decreasing, then in fact you can, huh? You can actually push it close to 1. Huh?
So it's not 1. It's not 1.
It is not 1. It has some non-trivial bound then. It has some non-trivial bound on the capacity. And you come here, you evaluate its capacity, go back all the way and calculate the actual capacity. That's the way you will do it.
Then you can use it to compute the non-commutative rank, or doesn't tell you full rank or non-full rank?
Can you use it to compute the non-commutative rank? Honestly, I don't know if they mention it in the paper. I'm not very sure. I have not read it. Yeah. Yeah. So this is the overall picture of the paper. And of course, I have not introduced the third character. I have had no time. But this is also a lovely paper actually, and which uses very much this. I mean, it really uses only this. Again, so the algorithm is very straightforward. Yeah. So this bound also, exponential of minus n, is very easy to prove if you know for sure your original space itself had a full rank matrix. Then you can actually calculate the capacity directly, because if it had a non-singular matrix, then Schwartz-Zippel lemma allows you to plug in sort of integers of reasonable value and get a matrix which has whose determinant you can actually estimate. Yeah? But if it is not, if there is no subspace, if there is no full rank matrix, then you have to do this tensoring operators to make sure at some point you will get to something which is. Yeah. Yeah. Sorry?
I'll ask you later.
Yeah.
So this or and like you have this
If
or and one and.
yeah, so this is one. If either it is, if I know it has been normalized either by column or by row, yeah, and I know eventually that it is close to this, then I can conclude that L is in fact non-rank decreasing. I can actually show that if I start with any matrix X, I will end up with a matrix of rank R, I will end up with a matrix of rank R.
Sorry, if n of y equals like or n star of y equals like. Oh, you want the other one to also be small. Which one? Okay. It's the one. Yeah, so one of them is 0. You want the other one to also be small.
Yes, you want the other one also to be small, exactly.
I think you only need a second condition, and you probably just need both of them to be really close to each other. You probably don't need one of them to be that way.
No, actually this, at least the way they prove this, it is under the assumption that it is normalized actually. If you don't work with if it is not normalized either way, it is not very easy to prove this theorem. At least I don't see.
The algorithm always ensures that the first quantity is.
Absolutely, that is an invariant, absolutely. The algorithm ensures this, yeah, but the lemma requires it. I mean, in some sense, the lemma, if I want to show that I am not rank decreasing, then I need to further assume that I am either normalized with respect to rows or normalized with respect to columns. Yeah. Yeah. Okay.
I have many questions already, but it's already. What questions? Okay, so I guess we can catch you.
Okay, sure. Yeah.
Let's thank you again.
Okay, thank you.